This video will talk about what to do if you want to add line segments or subtract line segments in a geometry. Underlying assumption here is that you have an incidence geometry where all the betweenist axioms are satisfied, and also all three of the line segment congruence axioms are also satisfied. So right now we have a total of 10 Hilbert axioms holding in this model, 3 incidence axioms, 4 betweenist axioms, and 3 congruence axioms. So let's go ahead and look at the definition of the sum of two line segments. So suppose you start off with two line segments, A, B, and C, D. And what we're going to do if we want to add these two line segments together is you pick one of the two line segments. It doesn't matter which one. I'm going to pick on line segment AB, and you look at the big complete line that this line segment is on. Now, technically, I'm going to go ahead and focus on array. In other words, we're just going to extend one of the sides of the line segment out to its full potential. Okay. Now, once you've gone ahead and started looking at the ray that this line segment AB is living on, notice here point A is the origination point of the ray. You can do it the other side, have B be the origination point as well. This works either way. Then what we're going to do is we're actually going to find some point E that's actually on our ray, specifically where BE and CD are congruent to each other. So notice what we just did right here. We actually used our axiom C1, that first congruence axiom for line segments, and copied our line segment CD onto the same line that AB lived on in the geometry. Now, this part here is critical. Notice what we end up having. We end up having in this orientation that point B is between points A and E. If we had extended out on this other direction, we would have ended up with point A is between points E and B. It doesn't matter which way you go. The key critical thing here is one of the endpoints on either that line segment A or B is in the middle there. In other words, so we're not going to do that way. In other words, all 3 points are on the exact same line. They're all distinct points. Now, notice what we have here. Since we copied the line, BE is congruent to CD. We already have the original line segment AB, and what this is going to tell us is that the sum of AB and CD is in fact this new line segment that we just created of A to E. Notice we actually had to move, or okay, you did technically move it, but you copied that line segment CD in order to create the full new longer line segment A to E. So that's what you do with adding two line segments. And in terms of notation, we go ahead here and say that AE is the sum of AB plus CD. Notice I went ahead and used the congruent symbol as opposed to strict equals just because we're dealing with line segments and technically we moved some things around there. All right, so associated with adding line segments are two propositions, Proposition 8.2 and 8.3. Proposition 8.2 basically says what we just did, you totally can do it. Okay, so what it says is you've got two pairs of line segments. AB is congruent to A prime, B prime. The primes here are not derivatives. It just says we were too lazy to think up of other letters, and we knew that A prime, B prime was going to be special because it was somehow related back to the original line segments A and B. Same deal with CD. We've got a second line segment CD. It's congruent to some other line segment C prime, D prime. Again, too lazy to think up of new names, so we just use the primes to indicate a second point associated with C, a second point associated with D. Now, the conclusion of Proposition 8.2 says if you'd find the sum of A, B, and CD, so if AB is here, and you've gone ahead and already moved CD over so that your C is now really over on top of B, and you've got your D over here. Technically, they'd probably be named something else, but let's just go ahead and do the moving over there. This new sum is however long it is. Okay. Well, if you have your A prime, B prime over here, notice that's supposed to be congruent to AB prime. And if we do the same moving around that we did to move C prime, D prime over on the elongated line segment where mine looks broken, pretend it's a real line. And if CD is congruent to C prime, D prime over here, notice that sum totally should be, or the two different sums that we calculated should totally be congruent to each other. This actually gives you what's known in math as a well-defined property. So addition is well-defined. What it means in practice is you're able to use some algebra, and if you have the sum AB plus CD, and you know AB is congruent to A prime B prime, you can substitute out the two things that are congruent to each other in your formula and do a little bit of algebra in the geometry formulas. Okay? So that deals with sums, congruence of sums. Now, the second proposition that's associated with sums is actually really associated with subtraction, which is highly related to adding. So in this, the setup is a little bit different. So here we're going to start off with 3 points, A, B, and C, where point B is between points A and C. And then we're going to have some extra points. So we've got here points E and F are on some ray. This ray starts at D, and I don't know where points E and F are on this ray yet, but they're going to be somewhere over here. So let's get their criteria. So the criteria that we need is that E and F, so E is supposed to be congruent to AB. So those two are supposed to be congruent to each other. And DF is supposed to be congruent to AC. So remember, AC is the sum. So let's visibly measure this out with my fingers there. So F should be, roughly speaking, right about here. Okay. Then the conclusion says that you get the picture essentially how we saw, that specifically point E is going to have to be between points D and F. So we're forced right here to show that we've actually got E is between points D and F. And you might be thinking to yourself, well, how does this get us to subtraction? Just a second, we're almost there. Because the second thing we get is we're also going to get that BC, notice BC over here, must be congruent to EF. And this is the part that gets us to subtraction of line segments. So that conclusion that the line segment BC and the line segment EF were in fact congruent to each other when we had those sums were congruent, and then the individual pieces of A, B, and DE were congruent, actually says, well, if you've got a part from the whole and the other part, BC here is in fact defined as AC subtract AB. So this is the subtraction part. And you could, if we looked at EF, this would be DF minus DE. And so getting this result of BC is congruent to EF tells you that subtraction is well defined, just like what we had with addition a second ago. In other words, we can take the longer thing, delete off a shorter piece of it, shorter side of it, and the remainder, that's your difference in terms of line segments.